So since making the video trying to explain this, I think I've come up with a simpler way to explain it. I guess it's called something along the lines of dynamic geometry is what Randall Carlson calls it. Now, I'm going to show the basic idea of how we get this, but we're going to focus on these rectangles. We start with a square, and we're going to focus on these rectangles. So we're not going to draw the whole circle or the squares around them. And we'll be able to understand how we're going from 1, radical 2, radical 3, radical 4, radical 5. We start with a circle, and inside of it is a square, and we would call the sides of that square 1. Now, as we explained, when we have a square with the sides 1 and 1, when we do the Pythagorean theorem, 1 squared plus 1 squared, or 1 squared plus 1 squared, is going to give us radical 2 squared. So this diagonal is going to be the distance of radical 2. So to create the next circle, we use that amount. And so we align our compass to that distance of the green line, and we swipe the arc, which means from here to that marking, or anywhere touching that arc, is radical 2. So we can actually continue this process and make another perpendicular line. I'm going to, instead of using a construction, I'm going to cheat here and use my perpendicular ruler. So now this rectangle here is going to have a top and a bottom of radical 2. So the nature of the Pythagorean theorem is 1 squared, this side here, 1 squared plus radical 2 squared is going to give us this diagonal. This diagonal gives us the amount of radical 3. And so we're going to do what we did a moment ago, and we're going to swipe that amount using our compass so we can find that distance here. So here we have radical 3. And so once again, we could use our ruler to make a rectangle, which means the bottom and the top of this rectangle has a distance of radical 3. And of course, these sides are always remaining 1. And so we can continue this indefinitely from here to here. This diagonal, we have radical 3 squared plus 1 squared gives us radical 4. And so again, we'll just adjust our compass to that distance, swipe it down, and now we know that this spot here is radical 4. So we could make another rectangle whose bottom and top are radical 4. Radical 4 squared plus 1 squared, as you can see, becomes radical 5 squared. So we can continue, like we said, this pattern indefinitely. And so then the way we would create the design we made, it's a little bit more complicated than this, but the basic idea, the way we would get the circles, especially the circle part, is we would take our compass, and instead of just swiping down to make a rectangle, we would continue and go all the way around and make a circle. Then we would adjust our compass to radical 3 and do another circle. And then adjust our compass to radical 4. And then after drawing the circles, we would use our straight edge to make the tangent lines. and you would see where they would meet to make a square. So we're going to draw the squares that are tangent to the circles, meaning it's going to touch the top, the bottom, the left, and the right of each circle. So as we make this green circle, we have a square that is tangent to it, surrounding it completely and kissing this point, this point, this point, and this point. So to actually create the square roots, as far as you are willing to go, really doesn't take long. However, the design where you making the full circles doesn't take long either, but the design where you make the square around it will take a few extra construction steps. And so I hope this shape is as satisfying for you as it is for me. I think it really puts another dimension on the geometry and actually the math that we study, because it helps you to see that square roots are not concepts, they're actual ratios and things that apply in real life, and we can visually represent them. Now, I've always found it fascinating that the number, like square root of 2, is an infinite decimal. Every square root that's not a perfect square, like the perfect square, square root of 4, square root of 9, square root of 9, square root of 16, square root of 25, those we can make them into whole numbers. But the others, like square root of 2, is 1.414, but it goes forever. Really like the number pi. But it helps you to understand, even like pi, it's just a ratio. For example, pi is the ratio of how much it is around the circle divided by how much it is across. And so wanting to understand math, I really find this quite fascinating. But as a builder, you know, you could quickly use this in your architecture to be able to find the proportions you're looking for in order to build things with the proportions that you would like. And you don't need a calculator to do square roots as far as proportions go. If you have any questions, go ahead and leave them in the comments, but I hope you enjoyed.